Okay, so good morning everyone. Uh, so today we will carry on our discussion of complexity of basic arithmetic operations. So last class we saw that addition and multiplication. So we saw the complexity of adding two numbers, and then we also saw the complexity of adding n numbers, that is iterated addition, and that essentially gives us a bound on multiplication as well. Okay. So today we will continue looking at other operations, other basic arithmetic operations, and try to analyze their circuit complexity. But before that, let me just formalize some circuit classes. So we have been actually talking about these circuit uh, classes, but we haven't formally defined them. So let me start by defining these bounded depth circuit classes. Okay. So essentially these classes consist of Boolean functions which can be computed by bounded depth circuits which have a certain structure. Okay. So the first definition that okay, that I want to introduce is that of non-uniform classes. So okay. So a function f from 0 1 star to 0 1 is said to be in the non-uniform class, let us say some C, some arbitrary class, if there exists a family of circuits Cn, okay, indexed by n. So basically by family what we mean is an infinite family. So C1, C2, C3 and so on, such that for all x belonging to 0 1 to the power n, f of x equal to c. Let me use a different index here, cm of x. Okay. So essentially we have been again, so we actually saw this earlier as well, but I am just formalizing this. Essentially this says that a general function, okay, so a function which can have inputs of arbitrary size. So I have a star over here. Now we say that this function is said to be computable, is said to be non-uniform C. So C can be any class if there exists a family of circuits such that for all x of a fixed length, okay, the value of that function on that input should be why do I have this was the comma, so yes. So the value of that function should be what the corresponding circuit outputs on that input. Okay. So this is what is non-uniform. So essentially the only thing that we are given is the existence of such a family. So this family need not be constructible, and we say that it is in uniform C if this family can be constructible as well. Okay, so we have notions of log space uniformity, we have notions of other uniformity as well. So logs, for example, if I say it is log space uniform, it means that this family can be constructible, I mean is constructible by a log space Turing machine. Yeah, so basically given n, so there is a log space Turing machine which given n can build Cn in log space. Okay, we'll come to that later. We don't need that right now. Okay. So, now moving on to some circuit classes. So, first let us say NCI. So, this is the class of Boolean functions computable by bounded Fanon circuits over, let us say, or and not having polynomial size and order log to the power in depth. So, NCI is all circuits which have bounded Fanon and polynomial size and log to the power in depth, okay, over and or not gates. Actually, this is not a very strict requirement. Even over any even over B2 also one can show that it can be reduced to circuits which have only and or and not gates. Okay. And NC is basically the union over all NCI for I greater than or equal to 0. So, typically we will look at the class NC1, NC2. So, NC1 is basically circuits which have log depth, NC2 circuits which have log square depth and so on. Now, we have the class ACI. So, ACI is exactly the same, but instead of bounded Fanon we allow unbounded Fanon. Okay. So, basically we can have an AND and OR gate which can take arbitrary number of inputs, okay. And the definition is of course very natural. So, if you have an AND gate with a k inputs, it outputs 1 if all the k bits are 1, and an OR gate with k inputs will output a 1 if at least one of them is a 1. Okay. So, ACI is the class of Boolean functions computable by unbounded Fanon circuits over OR and NOT gates having poly size and order log to the power in depth. Okay. And analogously, AC is union over all ACI for I greater than or equal to 0. Okay. So, before we go forward, let us just try to answer a few things. For example, last time we saw that addition. Okay, we looked at the problem of addition of two strings x and y. What is the so in which class is addition? What is the complexity of addition? It is in NC1 because we showed that it can be done by linear sized circuits having log depth, right. What about iterated addition or what about multiplication? again it is NC1 because we showed it is in log depth and it has polynomial size. So, I will actually come back to that problem a little bit later, but let me move forward. Okay. So, the next definition that we will see is about a function. So, these are function classes. So, let me define the threshold function. Okay. For x1 to xn belonging to 0 1. Okay, so, these are bits. This function threshold of x1 up to xn, let me just check the definition. Okay. Threshold of x1 up to xn is equal to 1 if a1 x1 plus a2 x2 plus an xn is greater than or equal to some theta and equal to 0, otherwise where a1, a2 up to an and theta does not depend on the x's, okay. But it can depend on n though. Okay, so, let me just explain this. So, what we are saying is that, so basically we have this threshold function which takes n bits and it will output 1 if basically this sum a1 x1 up to an xn is greater than some theta and equal output 0 otherwise. And these constants, so think of these a1 up to an and theta to be constants. So, they are constants because they do not depend on the specific input, they do not depend on the x's, right, but they can actually change with n. So, maybe for some n equal to 1 you have some a1 and you have some theta, for n equal to 2 you can have some different set and so on, but for the respective x's they do not change. Okay. So, they are constants for a fixed n. Okay. So, now we can define the class TC. Okay. So, TCI is the class of Boolean functions computable by polysize and order log to the power in depth circuits having threshold gates only. Okay. So, now if I say that a circuit, I will allow a circuit only to have threshold gates. Okay. So, TCI is basically all the functions that can be computed by such circuits which have polynomial size and log to the power I n depth. Now you might be wondering that what about other gates, I mean what about AND or NOT and these other basic gates. So the point is that any of those gates can actually be simulated using a threshold gate. Okay, so we can actually see that. So for example, how would you simulate a OR gate using threshold gate? Exactly. So you take the AIs to be 1 and theta to be 1. So setting for all I, AI equal to 1 and theta equal to 1 gives us the unbounded Fanon OR gate. Okay. What about AND? So an AND gate must have all its input as 1, right? Exactly. So basically for all I, you have AI equal to 1 and you set theta to be n. What about NOT? So a NOT gate will always have a single input. Okay. So what do you set A1 to be and theta to be? So one way to do it is, I mean there are many ways to do, but one way to do it is setting A1 to be -1 and theta to be 0 will give you NOT gate. Okay. No, A1 1 and theta 1 will not give you NOT gate. So it will be 1 if and only if xi is equal to 1 or x1 is equal to 1, and it will be 0 otherwise, right? It will be the same thing. Okay. So essentially the point is that, so threshold gates actually can, you can build any of these basic gates using threshold gates and probably more. Okay. So now, what about another, we can try another one. What about the majority function? So majority is when, so a majority gate will, the majority function outputs say 1 if at least n by 2 inputs are 1. Okay. Again it's simple, so you set all the AIs to be 1 and theta to be n by 2. Gives you the majority function. Okay, so now what are the relations among these classes? Okay, so we have these classes that we have defined, NCI, ACI, TCI and so on. So what are the relations? So by definition we have, what do we have? So we have that NCI is contained in ACI, right, because it's bounded, this is unbounded, and because we just saw that AND OR and unbounded AND OR and NOT can be simulated by threshold circuits, we have that ACI is in TCI. Okay. But one can also show that TCI is actually in NCI plus 1. So if you add another log n layers, you can actually not log n, actually you add another multiplicative factor of log n layers, then actually you can do TCI as well. And the way to prove this is, so I will just leave this as an exercise, this is not difficult. You can show that the threshold function, okay, so this is in NC1. Okay. So once you show threshold is in NC1, you can actually replace every threshold with a log n depth circuit, and then for any TCI you will get a NCI plus 1 circuit. Okay, and this you can think about it. Again, the idea is not very difficult, because so what are we doing? So essentially we are doing addition, we are doing iterated addition, right? We are multiplying with a constant and we are doing iterated addition and we are doing one comparison. So you have to think how you can do all of that. So iterated addition we have already seen, but comparison you have to think how you can do that in NC1. Okay. So any questions? I will just come to that. The answer is yes, you can do parity, and I will just come how you can do parity using threshold circuits. Okay. So before moving forward, just a small correction from something that I said last lecture. Okay. So last lecture what all did we see? Okay. So let me just quickly recap what we did last lecture. So we saw that given two numbers x and y, okay, let me just write that. We saw that given two numbers, we can do x plus y in what kind of complexity. So we saw that using this parallel prefix sum method, we can do this using a bounded fan-in. Okay, so a circuit which uses only AND, OR and NOT gates, bounded fan-in circuit having log depth and linear size. Okay, so this can be done in NC1. So this is something that we saw. What about iterated addition? So suppose if I have m numbers x1, what notation did we use? Did we use xi's or ai's? So what notation did we use last time for iterated addition? Xi's, right? Okay. So if we have m numbers x1, x2 up to xm, okay, where each xi is a n bit number, and we want to compute sigma xi. So what was the complexity of this operation? So what we said last time is that this is this can be done by a circuit which has order of log n plus log m depth, and how much was the size? So order mn. So this is what we said last time. Okay, but this is actually not quite correct. Okay, so actually it is size mn. So this log n factor doesn't appear, because just, I mean, let me just, if you just carefully look at the analysis, you will realize this. Okay, so let me just write it over here. So this is actually in size mn and not mn into log n. So the reason is, so how did we do this addition? Okay, so we have these numbers, right? So we have x1, x2, x3, 4, x5, x6, so on up to xm, and we took them in blocks of 3. Okay, and then we reduced this to two other integers. Okay, so we reduce the sum of x1 plus x2 plus x3 as the sum of some two other numbers, right? That is what we did. Okay. So, let us say in the second level we reduce this to something like x21 and x22. For this we got x23, x24, and the last one was m by 3. So, we will have something like x2 2m by 3 minus 1. Let me put a comma over here, and x 2m by 3, something like this, right. So, and to do this, okay, so here, so basically we are coming from, so here we are doing some m by 3 additions. Again here we will club them into groups of 3 and so on. So, how many additions will we have here? So, here we have a total of 2m by 3 numbers. Again we club them into groups of 3. So, we will have 2m by 9 many additions, right. So, we will have something like 2m by 9. So, in the next layer we will have, again we will do the same thing. So, we will have something like 4m by 27. Okay. So, essentially the total number of such additions will be sigma two to the power I m divided by 3 to the power I plus 1. Okay. This is actually the total number of additions, and if you actually solve this, so m comes out, what you get is sigma 2 to the power I over 3 to the power I plus 1. This is actually a convergent series. Okay, so this, I mean, in fact 2 to the power I plus 1 divided by 3 to the power I plus 1 itself converges to 3, right. So, this is actually even smaller than that. So, essentially this is order of m, and each addition we saw by the this method, that if you have any two numbers, each addition takes order n time. So, the total size is order n size. So, the total size is order nm. Okay. So, the calculation that we did last time, it was a very brute force calculation. So, for each level we assumed we have order m many summations, but that is not so. It is basically decreasing at each level. Okay. So, therefore, iterated addition can be done or can be computed by bounded depth, not bounded, what I want to write is bounded Fanon circuits in order nm size and order log n plus log m depth. Okay. Clear? One more very interesting point about this thing is that what is this size as a function of the input size? How much is the circuit size as a function of the input size? Is it linear? Is it quadratic? So, look at the input. We have m numbers. What is each number? How many bits does it have? Each number has n bits, right? So, what is the size of the input? it is nm, right. So, actually what we are getting is the optimal, okay. So, actually what we are getting is an nm size circuit, order nm size, okay. So, it is actually linear in the size of the input, right, and it has logarithmic depth. Okay.
Why is that depth log n plus log n? So each addition is
Each addition will take log n many log n depth, and
there are log n
the depth there are log m. So, this depth, okay. So, basically the way this addition works is you show that if you take any 3 numbers, okay, you can represent the sum of those 3 numbers as the sum of 2 other numbers, okay. So, you club them into groups of 3, and essentially initially you have a total of m many numbers, then in the next level you have 2m by 2m by 3 numbers. So, this is basically coming down one level, and now you keep on doing this. So, in the next level you will have 4m by 9, then you will have 8m by 27 and so on. So, basically this will, you keep on doing this until you have just 2 numbers left, and the number of levels you need to do this is order log n.
each addition is now replaced by a sum of two circles.
Which addition are you talking about? This addition?
Yeah, at each level.
Yeah.
So and there are log m depth.
Yes.
Many additions.
Yes.
Oh right, so yeah, addition.
Huh?
It should be addition.
Huh. Yeah, so this is something that I just wanted to clarify. Okay. Any other questions? Order of n square, yeah. No, it is not order of n square, it is order 2n actually. So, n plus n, right? No, but you are multiplying 2 numbers. Here you are adding, sorry. Sorry, yes, multiplication will be order n square, yeah. So, multiplication is still not optimal, yeah, correct. Absolutely. Well, the input size is twice n, exactly. So, you have two n bit numbers, so let us say you have x and y, which has size 2n, and you are showing that there is a circuit of size order n square which is doing. I mean, it is not optimal. I mean, I am not saying that it is not optimal, but I am saying that it can possibly be lower. Okay. Now, moving on to another very interesting result about threshold functions. Okay. So, definition. A function f from 0 1 to the power n to 0 1 is said to be symmetric if for all permutations sigma, okay, belonging to Sn, f of x1 to xn equal to 1, if and only if f of x sigma 1 x up to x sigma n equal to 1. So, essentially what this is saying is that a function is symmetric if no matter how you rearrange the input bits, it will have the same value, that is all. Okay. So, irrespective of the rearrangement. So, Sn is the permutation, I mean it is the basically the set of all permutations of size n. Okay. So, what we will show is threshold or not threshold. So, every symmetric function is in TC0. Okay. So, every symmetric function can be computed by a threshold circuit, by a TC0 circuit, basically that is by threshold gates which have constant depth only. Okay. So, the proof is actually not very difficult, it is just understanding how these functions behave. So, so given any function, okay, so given a symmetric function f, let us say, there exists a set S, okay, which has values b1 up to some bm, and these bi's are subset of the set from 0 to n. Okay, so let us say this is the, so do you use this, so is this representation used for the set from 1 to n or 0 to n? 1 to n, right? Okay, so then I will add 0 also. So, I will add 0 to it. I need 0 to be here as well. Okay. So, there exists an S, there exists a set B1 to Bm which is a subset of this, such that f of x1 to xn equal to 1 if and only if sigma xi, I going from 1 to n, belongs to S. Okay. So, let us try to just understand this equivalence over here. So, what is this saying? So, think of S as the think of S as being the number of ones, okay, on which the function f evaluates to true, evaluates to 1. Okay. So, f can actually evaluate to 1 on many inputs, right. Now, on all, just look at all those inputs and divide them into sets, or divide or partition them into sets such that in each partition you have equal number of ones. Okay. So, these are basically my B1 up to Bm. Okay. So, maybe there is some input on which I have no ones at all. Okay. So, that is basically the 0, and then I have some other input on which there are 2 ones, some other input on which there are 5 ones, and so on. But the point is that if I have one input which has 5 ones on which f evaluates to 1, then every input which has 5 1, f must evaluate to 1. That is by symmetric, because no matter how I permute those 5 ones, I must be getting the function must evaluate to 1. Similarly, if let us say f evaluates to 1 on again some other number of ones, it must evaluate to 1, no matter how you permute those quantities. Okay. So, that is essentially what this is saying, that there exists a set this, and now what I am saying is that if I sum the number of ones that are there in my input, that must belong to this set. So, there exists a set such that this is belonging to here. Okay. Is this clear? M is some number, M is an arbitrary number, it depends on the specific function. So, M essentially means how many ones are there, or wait, look, let me, how do I phrase this? So, M means that yeah, so how many ones are there on an input on which f evaluates to 1. For example, I will give you an example. For example, the parity function is actually a symmetric function, because no matter how you rearrange the inputs, it will always evaluate to true. Now, for the parity function, what will your S be? Any guesses? What will S be? The set of odd numbers. Okay. So, here the set S will be 1, 3, 5, 7. So, up to so we have n, right. So, let us say if n is odd, so it will be 1, 3, 5, 7 up to n. If n is even, it will be up to n minus 1, whatever. Okay. Exactly, that is what I said, the number of ones on which the function evaluates to a 1. Okay. That is the only thing that is necessary. Okay. So, now how do I write this? So, this I can write as, so this belongs to S. So, now S can have any value between this. So, this can be written as OR of let us say J belonging to S sigma xi equals bj. Okay. So, it means that there is some not j in S, but j in or bj in S, let us say, whatever way you want to represent this, bj belonging to S such that this is equal to bj. And now this can be written as how can you write this as a threshold function? So, I can write this as sigma xi. So, if my threshold function was greater than or equal to, right. So, this is greater than or equal to bj and sigma of minus xi is greater than or equal to minus bj. I don't need a thing. This is not needed. Okay. So, basically I am not doing anything fancy over here, I am just saying that a quantity is equal to another quantity if it is less than or equal to and it is greater than or equal to that quantity. And greater than or equal to, fine, I can represent it using a threshold gate, that is the definition of threshold. But for less than or equal to, I have just put negative, I am just switching the thing, I mean, to the other side, okay, that is all. And this is basically, so what we have is a depth. So, here I have a threshold, here I have one level, then I have an AND gate at the top, and then I have a OR gate. So, it is a depth 3 threshold circuit, depth 3 TC0 circuit of whatever linear size. So, as I said, immediately as a corollary, what we get is that parity is in TC0. Okay. So, now let us come back to this relation over here. So, for example, we have the parity function, we have showed that parity is in TC0. So, the natural question is to ask, is it in AC0 as well? Okay. And that is another, I mean, there is a sequence of very famous results which prove that parity is actually not in AC0, and we will come back to those proofs in the second half of this course. Okay. And they are not just proofs which showed that parity is in is not in AC0, but they actually developed very nice techniques. Okay. So, they actually developed very nice techniques to show that, which are useful for other results as well. Okay. So, which are useful for proving lower bounds in for other functions as well. Okay. So, this is kind of what we have. Okay. So, any questions? This we know is a strict containment once we prove that parity is not in AC0. Okay. So far we still do not know, but once we prove that parity, so we have just proved that it is in TC0, and once we show that it is not in AC0, it will be a strict containment, but this we do not know. We do not know of any function which belongs here but does not belong here. We do not even know whether this is a strict containment. We do not know if there is a function in, for example, which is in NC1 but not in TC0. We do not know that. We are showing for 0, yeah, so that is a good question, that does it generalize for any I? I am not very sure, but I think it should be true for any I, but I am not very sure. I cannot certainly say that yes, that is true for all I, but it is certainly true for 0. Okay. So, one exercise, in fact, I mentioned this earlier for you to try out, is to show that iterated addition is in TC0 in fact. Okay. Yeah. So, if you allow threshold gates, you can do it in constant depth. Okay. Okay. So, moving on. How? I think it is in AC0 because so addition of two numbers, right? Yeah, because if you look at yeah, exactly. If you look at that Cary-Lucahead adder, you can actually do it using with a bounded depth circuit which has unbounded fan-in. Yeah, that Cary-Lucahead adder is actually a AC0 circuit. Yeah. Okay. So, now we move to the next arithmetic operation, that is division. So, division is actually a very interesting operation for many reasons. First reason is of course that division need not be precise. Okay, so we can have two numbers such that if I divide one number by the other number, it may not have a finite representation, but essentially what we are looking for over here is just precision up to some n digits. Okay, we are just looking at the quotient which has a precision up to some n digits. So, the problem is we have input some x and y, okay, assume they are some n bit numbers, and what we want to output is, let us say, the ceiling of this. Okay. just the quotient. I mean you can actually, I mean once you get this you can actually show that you can also output the the value of the, I mean of the quotient up to some n terms as well, that is also possible, but whatever. Okay. And in actually what we will show is something a little different. So let me define another problem, reciprocal. So reciprocal is, we have input, let's say some number a, and what we want to output is one over. Okay, so we need some assumption over here. Okay, so this is let me just write this a little differently. So we'll assume that we have A such that A lies between half and it is less than 1 up to n digits of accuracy. Okay. So assume that A is a number between half and 1 and we are given A up to n digits of accuracy, and what we want to output is 1 over A up to the same accuracy. So what will be the value of 1 over A? Where will 1 over A lie? So note that 1 over A will be between 1 and 2. Right. So 1 over A is greater than 1 and it is less than or equal to 2. This is what we have, and this is what we want to output. And the reason why these two problems are somewhat equivalent is because computing x divided by y is the same as computing x into 1 by y, right, and x multiplied, and we know that multiplication is in, well, once we show this we know that multiplication is in TC0. Okay. So basically these two problems are what are called TC0 equivalent. Okay. So given, let's say, this problem, I can reduce it to reciprocal by using a TC0 circuit. Yeah, so what is the significance? So actually we will need this in our calculation, but the point is that this is actually not a very big restriction. The reason I will tell you why. So suppose you are given any number. Okay, so let's say that okay, let me write this properly. So why we can assume without loss of generality that is between this. Okay. The reason is, suppose you are given any arbitrary a, suppose any arbitrary integer a. What you can do is you can keep dividing a by 2 until it falls below 1. Okay. So essentially, given a, there exists a number k greater than, or it can be 0 also, yeah, greater than or equal to 0, such that a is equal to two to the power k into some a prime, such that a prime has this property. Okay. And how large is k? So k is as large as logarithmic in a. Okay. So essentially you can very easily create a log depth circuit which can do this for you. So it will take any number and it will keep on dividing it by 2. So it will find a number k such that dividing a by 2 to the power k will give you this required number. And then you do the entire process with a prime, and finally what we will do is we will just multiply it back with 2 to the power k and we will get the original reciprocal. Then you multiply it with something, you multiply it with, so you just, yeah, so if it is, let's say, less than half, then you multiply it with 2 to get it between this, the same argument. Okay, so now that we have this assumption, let's try to see how we can do division. So division is actually, there are many methods. So in fact, even our next lecture will be focused on division, but what we will show today is one of the very basic methods, and this is based on the Newton-Raphson approximation of any function. Okay. So consider the function f of x, which is equal to x minus 1 over a. Okay. So essentially the roots of this function is basically the value of the reciprocal. So for whatever value f of x is equal to 0, that is the reciprocal. So essentially what I want to compute is the root of this function over here, right? Is this. Now how do we compute the root of this? So what we will do is we will solve this in an iterative fashion. Okay, so first we will guess some value, we fix some arbitrary value as my root. Okay, so we start with some x naught. Okay, so we start with some x naught. Okay, then okay, so we start with some x naught, okay, as the initial estimate, and as I said, use Newton-Raphson's method to get better approximations. Okay. So how do we do? So we all know this. So let's say we have some xi. So xi plus 1 will be equal to xi minus 1 second. Okay, fine. F of xi divided by f of x, f prime of xi. Okay, so this is how we get closer and closer approximations of the root. And now what is f prime of xi? So we know that f of xi is x minus a of I. So this is nothing but, if I look at the first derivative, it will be yeah, this should be actually one over x minus. Okay, so we'll take fx to be this function 1 over x minus a. Yeah. So then this will be xi plus f so fxi is nothing but 1 over x minus a. Now divided by the derivative of this is minus 1 over x square. So this becomes a plus and I get x square over here. Okay. So this is equal to xi plus xi minus a xi square, which is equal to xi 2 minus a xi. Okay. So basically to compute xi plus 1, I need one multiplication over here, then one addition or subtraction, whatever you want to call it, and another multiplication. So basically two multiplications and one addition. Okay. So now the question is, how many times do I have to do this? So I want, so as I said that I want to get the value of 1 over a up to the same level of accuracy. Okay, so I start with some initial estimate, and let's say I do this once, so I will get x1, x2 and so on, but how many times do I need to do this? How do I estimate the accuracy? So first of, okay, so let's say, so what is the initial value? So we start with x0 equal to 3 over 2. Okay. So if we start with x0 equal to 3 over 2, yeah. Now let's calculate the error term. Okay. So we will calculate the error term after each iteration. So what is the error term initially? So initially I will have epsilon 0, okay, which is equal to okay, 1 over a minus x0. So x0 I start with 3 by 2. Okay. So if x0 is 3 by 2, then 1 over a minus 3 by 2 is, so 1 over a I know is between. So error term means that at every step I calculate xi. How far is xi from 1 over a? What is the difference between 1 over a and xi? Okay. So that should converge, and that should converge quickly for us. So we have to show that in a small number of iterations, I should get accuracy up to n bits. That is what. Okay. So okay, so let me just write this. So the error term, let's say after the ith step, it is EI is defined as 1 over a minus xi. This is the error term for us. So initially this is 1 over a minus x0. So 1 over a is between 1 and 2, and I take x0 to be 3 by 2, that is 1.5. So this is basically less than half for us, less than or equal to half. Now we will try to estimate what ei plus 1 is, or epsilon I plus 1 is, in terms of epsilon I. Okay. So what is epsilon I plus 1? So epsilon I plus 1 will be 1 over a minus xi plus 1. And what is xi plus 1? Xi plus 1 is in terms of xi, it is minus 2xi plus a xi square, and if you actually rearrange this, what you will get is a into 1 over a minus xi whole square, which is equal to a epsilon I whole square. Okay. So essentially, and what do we know about a? So we know that a is less than 1. So therefore this quantity is less than epsilon I. Okay. And not just, yeah, so and not just it is less than ei, essentially the error actually reduces by a factor of quadratic. Okay. So at each level the error kind of I mean the number of precision digits in 1 over a actually doubles. Okay. So after each iteration, the number of precision bits in x I doubles. Okay. Because I have a quadratic factor over here. If there is a cubic factor, then yes, it would triple, the number of bits will triple. Okay. Huh? Exactly. So we only need log n many levels to get to a accuracy of n. Okay. That is exactly how it works. Therefore, in order log n iterations, we get n bits of accuracy, and that is what we want. So essentially, what is this thing now? So we do this in an iterative fashion. So at each level we are doing essentially multiplication and addition. Okay, so that is like So, if you are looking at NC circuits, that is like log depth for us, and here we have another additional log depth. So, therefore, division is in NC2. Okay. So, this gives us an NC2 circuit for division. So, now the question is, can we do better than NC2? Can we do it in, for example, in TC? Huh? Where?
Why is it getting multiplied by log n?
Oh, because we have to do this multiplication. Na? So, sorry, this one. So, from xi to go to xi plus 1, we are doing multiplication and addition. We know that multiplication takes log n, and this we are doing log n time. So, that is why we get log square. Yeah, so next we will see how we can improve upon this, how from NC2 we can actually come down to smaller depth circuits. Okay, so I will stop here today.